I'm Marc Stein. I am the founder and CEO of Underwrite.ai. And what we do is we do nonlinear modeling of credit risk and also cancer risk in genomics. The reason why we do what we do is that when I sold my last company and was wondering what I was going to do next, it occurred to me that most of the serious problems in the world are inherently nonlinear. We live in a highly complex world. Because human beings really like to kind of dumb things down and think of things in terms of binary rules, we address these nonlinear problems with linear models. And a really good example of that is credit modeling. So when you, let's see, is this running? Can you see that? Okay, good. Typically when you model credit in the United States, you look at the FICO score, the debt to income ratio, the trade line count, so how many 30-day lates, and the inquiry count, how many times have people asked for credit. You build a very simplistic rule scorecard. If they've asked for credit more than 6 times, you don't give it to them. If they've had a 60-day late, you don't give it to them. If their FICO score is below 660, you don't give it to them. If their FICO score is above 660, then depending upon what their FICO score is, you set an interest rate. That's 99.9% of lending in the United States. Our question was, well, that works very well for the segment of the market that is FICO 700 and above, because you've largely de-risked the population. But what about the 700 and below? What we discovered was that FICO and that approach is less and less effective the further you go from the 700 breakpoint. So our question was, well, what if instead of looking at 4 attributes, we looked at 1,000, 2,000, 3,000 attributes? Do we get a better predictive model? And the answer was yes, we very much do. And that work actually derived from work I was doing in genomics, where we were trying to predict cancer risk of prostate cancer. And we were looking at the RNA microarray data. So when you get an RNA microarray, you have 25,000 gene expression levels. And the way that modern diagnostics deals with that is to isolate 9 or 10 genes that are considered biomarkers for prostate cancer, create a panel that reads out the expression levels of those 9 or 10 genes. This works to some extent. I mean, the accuracy rating is in the high 70s, right? Which is a little bit better than a pathologist looking at a microscope, but still not very good. So the question was, well, what if instead of trying to identify 9 biomarkers, what if we looked at all 25,000 genes and looked at them in a combinatorial fashion? Could we improve upon the state of the art? And what we discovered was there aren't 9 genes that are correlated to prostate cancer. There are 2,400 genes that correlate to prostate cancer. And that we can achieve an accuracy in the 90s as opposed to the 70s by looking at more data. So that discovery led to, well, how do we apply this in finance? And the reason for applying it in finance is just like the ineffectiveness of cancer diagnosis is a major societal problem. Another major societal problem is the lack of credit availability in underserved markets and underserved communities. And we have people in the United States who do not have credit availability. About 20% of people in the United States have no FICO score, have no ready access to capital. You know, we're working in the Philippines. Well, 90% of people in the Philippines don't have bank accounts. They have no access to capital. In India, which is quite advanced, you still have 70% of the population that really doesn't have access to capital. So this is an inherently nonlinear problem which we're not going to solve with logistic regression, and that's what we knew. So the real motivation behind it was I want to change the dynamic about credit availability in underserved markets. And the way to do that is to convince investors that it's profitable to loan money to underserved markets. Because if the yield is there for the investors, they don't have to be good guys about it. You know, we can appeal to their greed and we can fund projects that expand the access of credit throughout the world. So I wanted to give, a couple of examples of very different credit systems and how nonlinear models compare with linear models. So the Korean credit market is fascinating because Korean people are really obsessive about paying debts off. The default rate in Korea is extraordinarily low. And consequently, the interest rate in the Korean market is very low. This is how credit is derived in South Korea. You have these 4 basic buckets, and then there is a logistic regression model which utilizes these 4 buckets. So it's a little bit different than the US model, but it's the same conceptually. Simplistic model, logistic regression. And this is the distribution of credit in Korea. So you can see this, the first green band, tier 1, are people with exceptionally good credit. And you can see that's the largest segment. As you go around, green, it gets a little lighter green. These are people with good credit, and then good credit, but not quite as good. Then you get into yellow. And all of this circle, with the exception of red, has credit availability in Korea. Korea utilizes a model which assigns 10 credit grades, 1 through 10. And basically nobody loans to 7 and up. This is the efficiency of the current model. So here you have a highly efficient capital system with a highly efficient model. The AUC of the existing 10-level credit scheme is a 0.9. So anytime we see a 0.9 in a model that we develop, we go back and look to see where we made a mistake because that's really, really too high. So this is a logistic regression model that works really well. It utilizes a small feature set very efficiently. So the linear model is quite performant. They don't really have a problem in South Korea. So the question was, well, could we improve upon the status quo in South Korea? So we went to the bureau in South Korea, and they very kindly sold us a large amount of data. And we said, well, what if we take a nonlinear approach and use H2O and DAI to model the problem? So are there gains to be had by replacing 4 variables with 763 variables in a combinatorial manner using DAI? So these are the results. So you can see that DAI went through and tested 16,749 features, selected 210, built a final pipeline, and you can see the AUC that we achieved was 0.95813, which is the first time I've ever had a model be 0.95 and not spent the next 2 hours trying to search for the extra dependent variable that got put in there. So when we compare the efficacy, we see that even in a situation that works really, really well, you can still apply nonlinear techniques to improve upon it. So the takeaway for me was that a highly efficient logistic regression model can be significantly outperformed by a GBM model, which incorporates more data and uses feature engineering to combine data. And I want to look at a less efficient model that'll probably be a little more familiar to most of you. And that is a US case study is a large consumer lender with an overall charge-off rate of 8.6%. So 8.6% of the loans that they issued don't pay back. That's fairly typical of large online lenders. not as typical of a large bank that only lends to very prime customers. When we looked at the models inherent in this lender, we took their interest rate model and looked at the AUC of it, and it's 0.68. We saw that their model, which incorporates FICO, outperforms FICO because FICO is 0.669. What that tells us is they've done a good job at building their model. Anytime they're outperforming FICO, that means the things they've added on top of FICO are actually predictive. And nobody ever got fired as a chief risk officer for overperforming FICO. Okay? CV Link is an alternative data product from TransUnion that contains additional data points, and their score slightly underperforms the interest rate model. But the nonlinear model that we built has an AUC of 0.82. So anytime, we're relatively happy with AUCs in the high 70s. The low 80s is fine. So we're really happy with, with this performance. If we look at the performance by rate tier, this is what gets interesting. This is the slope of default by their interest rate tier. So you can see their model is quite linear and works fairly well. The first tier defaults at 1.9%, the highest tier at 15.54. If we look at it by deciles, we see that, you have 6 tiers and 10 deciles, so it becomes choppy. But you see the same basic slope. This is the slope by FICO. So FICO is grouping 21% of the loans in the 10th decile. That's actually an improvement over their model at the low end. This is CB Link, very similar to FICO. But this is what happens when we build a model. Because our goal in building the model is we want to cluster the greatest percentage of defaults into the highest price tier. So we want, our ideal model is a flat line to the 10th decile and then a hockey stick, right? We're not quite there yet. But what you can see here is with AI as the gold line, we outperform the legacy models for the entire duration and then spike at the 10th. This is what we're after. So the takeaway here is that the GBM ensemble model significantly outperforms all the linear models in use at this lender across the full slope. So now that I got that out of the way, let me talk for a minute about genomics, since that's what most people are interested in. When I first sold the last company that I was involved in, which was a company called LeaseQ, it was a marketplace for equipment leasing. And I wanted to start a new company, and I didn't want to raise money, so I took the payout from that company and rolled it into this one. And I was looking for what to do, and I got interested in nonlinear problems. And the first one was cancer diagnosis, particularly prostate cancer diagnosis, which I picked because it has the lowest accuracy rate of any cancer diagnosis. It's a really hard problem. And the way that cancer is diagnosed is that, or prostate cancer is diagnosed, is that they take a blood test from a male and they measure the prostate-specific antigen. And if it's elevated, they suspect that the person has or may have prostate cancer. Now, the problem with the PSA test is it works about 50% of the time. Which means if you really want to know whether you have a probability of prostate cancer, you could also flip a coin. But nobody's going to go to a doctor who flips a coin. So that part's not real good. But if somebody has a positive reading for PSA elevation, they generally get sent for a biopsy. And the biopsy consists of a fine needle aspiration into the prostate, which takes a number of samples and sends those samples to a pathologist. The pathologist looks at these samples through a microscope and tries to detect whether they see tumor cells. Now, logically, you can immediately see the problem with this. If cancer is early stage and not well dispersed throughout the prostate, the likelihood of you sticking the needle in a tumor is low. So what are you going to actually discover? Well, you're probably going to discover a lot of late cases, more so than early cases. And that's just basic math. So the question that I was asking was, well, what if we didn't have to look for tumors? What if we looked for genetic signatures anywhere in the prostate, so that no matter where you took a sample from, we should see an elevation of the signature to tell us that prostate cancer exists somewhere nearby? I didn't realize at the time that that was a really radical idea. It seemed to make sense. And we found that we could get samples of stromatic tissue, that is a tissue from the prostate that is not cancerous, that is nearby, for both non-cancerous cases and cancerous cases. And we could analyze the gene expression levels. And the way that we would do that is you send the tissue sample off, you extract DNA, you then move to RNA, and you send it through an Affymetrix device that basically gives you a readout of all the gene expression levels. Then you normalize that, and that's what you end up with. What we started doing then is, well, let's take that and let's run it through a machine learning algorithm for all the cases that we could find. Then we discovered a problem. When you have 25,000 columns in a spreadsheet, there aren't very many AI programs that like that model. When you have 25,000 columns and 100 cases, the problem is compounded. So we started working on techniques for how could we feed a vector of 25,000 in, at least to the point where we could discern what could be thrown out. So we found that information game theory would allow us to determine what could be safely removed, and that allowed us to get 25,000 down to about 2,400. Then we can start building combinatorial models on the 2,400. And we found that using this approach of working with non-cancerous tissue, we could achieve accuracies in prediction in the 90s as opposed to the pathologist's 72% hit rate. And the next stage, and I've been trying to talk to people about getting case samples, is that what if you could do this with blood, right? What if, because we can extract DNA from serum, and we can see traces, we can see the genetic expression in serum, but more importantly, we can see microRNA that will give us an indication of cancer. And we just finally got a model to run successfully that had 465,000 columns of proteins. Because I think the real answer is to measure protein levels and microRNA more so than genes. But the point really is that whether we're talking about credit modeling or we're talking about genomics, we're talking about the same thing. We're talking about highly nonlinear problems that are much better solved by using nonlinear algorithms. And that most of these problems are approached throughout the world with linear solutions, and that it doesn't work well. If we go back to the credit space, when I said that the credit market, in the US, about 50% of credit is FICO 700 and above. So how do you effectively provide credit to people who don't have FICO scores? And that's what we've been focused on. We've also gone into the Philippines to use these same models because we want to see if we can lend to people in the Philippines who are really hamstrung by the fact of an average salary of about $2 a day? Can we provide them money to start businesses and to provide medicine for their family and get it paid back? And can we do it profitably? And how do we measure the risk? So these are, to me, examples of nonlinear problems. And the world is just full of them. And the beauty of something like H2O and DAI is it empowers people to solve this very disparate range of problems. And if you think about all the problems in the world that are really serious, and you start thinking about whether they're linear or nonlinear, you can start to see the opportunity that machine learning offers. How are we on time?
2 minutes ago.
2 minutes. Do you want to take some questions?
Actually, we're running out of time for questions. So.
Oh, okay. Well, we have 2 minutes.
No, but
okay.
If you were to speak, like we could give it 2 more minutes, but
okay, we'll leave it at 2 more minutes. So that's the basic idea. The first question that I really ask when someone comes to me and say they want to start a company is, the first question is generally, well, what are you planning on doing? The second question is a much more important one, which is why. And I think that the important part of applying nonlinear models is in the why, in that we can solve a series of problems that up until now have been largely insoluble. Thank you.
thanks, Mark.